Hello to everyone, I'm Andrea Chiocca, an assistant professor at the University of Pisa. Today I'm going to present some optimized methods we developed for evaluating efficiently critical plane factors. So, the efficient calculation of critical plane factors is of major importance, as these models allow to perform a multi-axial fatigue assessment under non-proportional loading conditions. These damage models are quite used in academia research environments. However, they're not so used in industry because a withdrawal of these methods is the computational inefficiency. So, what does it mean? If we want to perform a fatigue assessment using, for example, finite element analysis, then the evaluation of a critical plane factor for a single node of the simulation can require around a second. So when we think about performing the analysis for big models, so having 1,000 or 100,000 or millions of nodes, then the analysis can be a lot time consuming. So already we can find works in the literature aimed at reducing and more efficiently calculating critical plane factors, both in frequency domain and in time domain. Also researching some adaptive algorithms for identifying critical plane factors. The logic of our methods is quite different from the ones that I showed before. But before going deeply in explaining the theory behind the method, then I want to introduce generally how we can define critical plane factors. So, broadly speaking, we can have two different categories of critical plane factors. So, the first one, where we need to maximize a single parameter in the formula. That can be, for example, a stress-related parameter, a strain-related parameter, or a combination. And in this category, we can find Fatemi-Sossi or Smith-Watson-Topper, for example. Another category is requiring the maximization of the entire formula of the critical plane factor. Again, we can find another formulation of Fatemi-Sossi and, for example, the Findlay critical plane factors. So on the first category I mentioned, that we published recently a paper, and this is the method I'm going to present deeply today in this presentation. Other two methods are under development to be able to efficiently evaluate all the critical plane factors that are inside the second category I explained. As a case study for explaining the method, I will use the Fatemi-Sossi critical plane factor. So why the Fatemi-Sossi critical plane factor? Because this kind of critical plane factor can be found for both categories of the flowchart I showed before. In these slides, these are shown as the two formulations of Fatemi-Sossi critical plane factor. So the model already published is based on the first formulation of Fatemi-Sossi, so where the delta gamma maximization is required. So we are looking for the plane where the delta gamma is maximum, and then we have to find the normal stress to this plane, so the maximum normal stress to this plane. In the second formulation, and this formulation is related to the new methods under development, is requiring the maximization of the entire formula of the critical plane factors. So we are no more looking for the plane where delta gamma is maximized, but we are looking for the plane where the entire formula of the parameter is maximized in this case. It is quite important to mention what is the standard way of evaluating critical plane factors. So if we think of having a component, a loaded component, using, for example, finite element analysis, then we can select a node, and then we can perform the following action for each node of our component to evaluate the critical plane factor for each node. So first of all, we have to select a plane, and on this plane then we have to evaluate the quantities that can be stress-related, strain-related quantities needed to calculate the critical plane factors. And then we have to rotate this plane through a step-based analysis. So we have to rotate the plane, and on each rotated plane then we have to re-evaluate these quantities. At the end of this step-based rotation, that usually is performed through some forehand loops, then we have to calculate the maximum parameter of critical plane factors. What is the problem here is that we just need the maximum parameter, but during this evaluation we perform the analysis and we are evaluating a lot of quantities that are not needed. And this is quite time consuming. So the efficient method we developed is skipping all the non-necessary evaluations and is directly evaluating the maximum quantity, so the critical plane value. So as I already mentioned, this kind of formulation, the plane scanning method, is requiring usually around 1 second per node. In our case, we implemented this method in MATLAB, and we reached about 0.8 seconds per node. So that it's quite a long time when you think of evaluating millions of nodes in a model. In order to verify the correctness of the efficient methods, then we use some finite element analysis on 3 different geometry of specimens, so an hourglass specimen, a notch specimen, and a welded joint specimen. We performed different loading condition analysis on each specimen, so each specimen was loaded with proportional and non-proportional loading condition. So if we take, for example, the hourglass, then we perform a simulation of fatigue loading, only tension compression, only torsion, and tension and torsion. The same we did for the notch specimens, and for the welded joint we perform simulation just in bending, torsion, or torsion bending loading condition. The basic assumptions that are required in order to use the efficient methods are that the load time history is discrete. What does it mean? We developed the methods in order to be applied in a finite element analysis. So for us, the load time history is discretized through a load step of the finite element analysis. What does it mean? That we can define easily a stress and strain tensors related to the generic Heath load step or the Heath loading condition of our load time history. In this scenario, it is easy to define a tensor range that can be a strain tensor range or a stress tensor range. So in this case, here it's shown the strain tensor range, and this is defined as the difference between the strain tensors between the 2 different load steps. So this is the formulation of our strain tensor range, and from now on we will use this definition to explain the efficient method. The efficient method can be easily explained in the Morse notation, as you can see here. So for each tensors we defined, in this case it is shown the strain range tensor and the stress tensors related to the 2 different load steps, Heath load step and Heath plus 1 load step of our finite element simulation. So for each one of these tensors, we can then draw the Morse circles. And using the Morse circles, we will see in the next slides that it's easy to explain the methods we developed for efficiently calculate critical plane factors. Let's go deeply in explaining the efficient method for the first formulation of the Fatemi-Saucy critical plane factor. let's start by extracting all the stress and strain tensors from the finite element analysis for each load step we are interested in studying. So here you can see the elementary cube of material where we reported the strain range tensors quantities on the cube. So in this first case, then if we take this direction, this can be, for example, the direction of the global reference frame of our simulation, then we will be in some points inside the Morse area. Okay, let's go on. We now rotate the reference frame in the same direction of the principal reference frame of our strain range tensors. So in this case, for our strain range tensors, we can, for example, be on this face that is represented by this point, so representing the face where we have the maximum principal strain range quantity. For our stress tensors, then we will be somewhere always inside the Morse circles, depending on the orientation of this principal reference frame. And then finally, we can start rotating our reference frame around the middle principal axis. Doing this, then we will move on the outer circle of our delta epsilon tensor, while we will, say, generally move inside the stress tensors in the Morse configuration. So let's take for Fatemé-Sassi, for example. For Fatemé-Sassi, we need to maximize delta gamma. To maximize delta gamma, we have to easily rotate until 90 degrees, and we will find directly our delta gamma max. And using the reference frame after a 90-degree rotation, then we can extract the values of the maximum normal stress for both load steps. At this point, we have just to evaluate which is the maximum between the two, and we can directly evaluate the critical plane factor value. In this case, for the case study of Fatemé-Sassi critical plane factor, the delta gamma is maximized after 90 degrees rotation, and this maximum value of the normal stress is just a maximum formula applied to these two quantities. So, as you can understand, we just skipped a lot of plane rotations and evaluation on each plane about these quantities, and just going directly in evaluating the quantities needed for the critical plane factor. From a graphical point of view, it's quite easy to understand how more efficient is this method to respect the standard one by looking at these results. So here you are seeing the delta gamma calculated for the notch specimens under three different loading conditions. So tensile loading, torsional loading, and then combined tensile torsional loading. Here I plotted a surface that is related to rotating on different planes, and on each rotated plane, then we evaluate the delta gamma max on this plane. So you can see here that the standard way of evaluating critical plane factors is requiring evaluating the solution for a lot of points, and how many points are these is depending on the angular step we are selecting. For our efficient method, instead, we had just to evaluate this single point, and doing this, we are saving a lot of time. So by implementing both codes on MATLAB, then we are decreasing the computational time of order of magnitudes respect the standard scanning plane methods. And this can be quite important when we want to evaluate our critical plane model for complex, for example, models, complex both in geometry and loading condition, where it is difficult to understand where is the critical region beforehand. And then we need to do the entire evaluation of the model, and then understand the critical region after that. Being the method based on tensor math can be easily implemented in different codes. So at the moment, we implemented the codes directly in MATLAB. So here you can see the different specimens where we mapped the critical plane factor of Fatemi-Solsi for all the specimens. So you have to think that each specimen here had 1,000 of nodes, and mapping all the critical plane factor all over the specimens required not so much time. We can usually it was around like a minute for each specimen. The code is also implemented inside ANSYS APDL code, and through this implementation we are now able to implement directly the critical plane factors we need inside ANSYS Workbench, and directly plot so mapping all the nodes of our model with the critical plane factors we need inside ANSYS Workbench. And also implementing the code directly in ANSYS is saving a lot of time because we don't need to extract all the results from ANSYS and then to post-process them in another software. To conclude the presentation, we developed an efficient method that we already published to evaluate efficiently critical plane factors that are belonging to the first category I mentioned in the beginning of the presentation. So whenever a single parameter maximization is required inside the critical plane factor formula, other two methods are under development for evaluating more efficiently critical plane factors that are belonging to the second category, so where we need to maximize the entire critical plane factor formula. So all these methods, so the one that I present in this during this presentation is based on analytical formulation. The other two methods are based on one on analytical formulation, the other one on a numerical simulation. In all cases, we can reduce massively the computation time that is required for evaluating the critical plane factor. The math that is behind these models is quite easy, and this way we can implement the method in mostly every code. So we already did it for MATLAB code, for ANSYS APDL code, and we are trying to do it for Python and to be able to implement the code also in Abacus. So I thank you for your attention, and I am open to questions to my contact, so mail contact or telephone contact. Thank you.